All right. Hello, wonderful people. Let's see. Moving on to what we got going on today. So graph linear inequalities and determine solution areas and apply graphing inequalities to solve real-world problems. Okay, so that's our objectives. So what do we need to know? Well, think about it. A linear inequality is similar to a linear equation, but we use the inequality symbol instead. So if I have something like this, this is a linear formula. It's got the y, the equals, the mx, and the plus b. Remember that this math, in order to be true, has to be open towards the bigger number. So I'm gonna have to do some plugging in. So if I have x and y like this, well, is it gonna make it true or false? So let's go ahead and try some of these and I'm gonna see what we get. So I have y or x. In this case, x is 7, but I need the y first. So in this case, I need 4 is greater than or equal to. Now I can't write the or equal to, so we're just gonna have to kind of pretend that it's there. And then x here, we have x is 7. So I'm gonna plug a 7 in where x used to be, and then keep the plus 9, that part hasn't changed. So 4 is greater than, and then I'm going to multiply these two together. Negative 2 and 7 would be 14. And then here I have 4 is greater than, let's see, what would this be? This would be negative 5. So in this case, that would be, well, true, right? Because this is going to be true. So yes, it is a solution. And remember, even though 5 is normally a bigger number, positive numbers are always greater than negative numbers, right? Is it better to have $4 or to owe $5, right? So it's better to have $4 than it is to owe somebody $5. So let's go ahead and move on to the next one. And again, there is an X value and a Y value in here. So I'm gonna have to substitute both of them in. And let's try that out. So y is now 3. So 3 is greater than negative 2 times, and our x value here in this case is negative 1. So let's see if this works out. So 3 is greater than, and then I have negative 2 and negative 1. So negative 2 times negative 1 would be positive 2 plus 9. And then 3 is greater than 11. So this here is a false statement because they're both positive, right? And then the bigger number would be the greater number. But in this case here, this is false. So this is not a solution. This will not work because this gives us a false statement. And it's only a solution if it works. Remember, that's what the solution means. It's what you have to put in to make it work, or in this case, make it true. Just like fixing a car, right? If your car is not starting, changing the tires is not going to help. That's not a solution. All right, so last one for this thinking about it example. So y in this case is negative 5. Greater than negative 2 times, and then here we have our x value, which is 10 plus 9. All right, so let's go ahead and keep going with this. Negative 20 plus 9. Negative 5 is greater than, let's see, 9 minus 20 would be negative 11. So in this case, they're both negative. So what happens if they're both negative? Well, if they're both negative, we want the one that is smaller, or what would normally be a smaller number. So thinking about it this way, would you rather owe somebody $5 or would you rather owe somebody $11? In this case, it's better to owe somebody $5 because you don't have as much money to pay back. You don't have to pay back as much money. So in this case, that is a true statement. Our mouth is open towards the greater number in this case, which is negative 5. So that is a working solution. And again, solution is what you put in to make it work. All right, so that's kind of just a warm up. Let's go ahead and move on to the next one and thinking about an actual real world example. So this is an example of what they call breaking even or making a profit. So, okay, think about it this way. Let's say you wanted to make some money, right? And you just managed to get a place where you can sell, let's make it easy. Let's say snacks, okay? So you decide to go somewhere, go to a store, a big store maybe, and you decide to buy as much snacks as you can, you know, whatever you have, popcorn, chocolates, whatever you think people would like. And you try to buy it for as low as you can so that when you sell it, you know, the extra money you get is in your pocket. So if you buy $20 worth of snacks and you don't really sell that much, then you basically lose all that money. Well, you'd get a lot of chocolates, but you don't get any money out of it. And if money is what you're trying to get, then you kind of didn't really you didn't really fulfill that. So that's what we call breaking even. When you make enough money, just enough to cover the cost, because running a business comes with a cost. You know, buying the supplies to sell is a cost as well. So in this case here, John sells t-shirts. Plain shirts cost $5 and graphic shirts cost $7. In order to match his product cost, he must make at least $1,200 or $1,200. All right, so again, if he doesn't sell enough shirts, he can come up at a loss, meaning that he owes more money on his supplies and machinery than he does making the money. And if you keep doing that, you're going to run out of business, run yourself out of business. And I know you've probably seen stores and restaurants run out of business because they're buying more stuff than they are selling. Anyway, so let's go ahead and write an inequality. So let's go ahead and make this one a little bit of an easy one for now. And anytime I do word problems, I like to pick ones that manage to keep things simple. So 5p, so $5 per plain shirt. So if he sells one, that's going to be $5. If he sells two, it's going to be $10, and three would be $15, and so on. Now, the graphic shirts are a little bit more. Now, we're not really concerned with cost. So in this case here, he is making money of $7 on each shirt. Now, he wants to make at least $1,200. Now, normally we'd put a equal sign here, but we don't need the equal sign for now. We need an inequality. So it could go this way or it could go that way. So think about it. Which side is the better side? Which way does the mouth open? So think about it this way. Which number do we want to have be bigger? Now think about what each side represents. This is his production cost. This is how much money he makes. Which side do we want bigger? We want the side of how much he makes to be bigger than his cost. So that means the mouth is going to open towards the P and the G, right? So we want this side to be bigger. So that means this is facing the right direction. Now we're going to go ahead and use our equation here and answer these other two questions. So if he sells 150 plain shirts and 60 graphic shirts, will he be able to cover the production cost? All right, so 5 times 150 plus the number of graphic shirts he sold, so $7 a piece, and that's 60 pieces. And we want this to be greater than 1,200. Okay, so let's see, what is 5 times 150? So that's like 5 times 15. So 5 times 15 is 75. Put the 0 back. And again, same thing, we're going to do this. We're going to ignore the 0. 7 times 6. 7 times 6 is 42. Bring the 0 back. And we're going to add these two numbers together. So I'm going to go ahead and, so 750 plus 420, that would be 1,170. So in this case here, he came out at a loss because his cost to set up the shop and buy all the shirts is about $1,200 or 1,200. Which is kind of a weird thing, actually. This is kind of an off-subject thing, but why do people say 1,200? I mean, I guess that's better than saying 1,200. I guess it goes by the years. I mean, that's kind of my guess. Like when people say, you know, the 8th century, the 9th century, the 10th century, the 11th century, you know, you'd say 1100 AD or something. I don't know. That's just my guess. Anyway, so in this case here, the answer is no. He does not cover his cost. So in this case, he goes home at a loss if he stops now. All right, so let's see. In this case here, it says here he sells 90 graphic shirts. What is the minimum number of plain shirts he must sell to break even? So maybe he had a big order. So when he opens his shop, he notices that he got a big order in for 90 graphic shirts. And to keep from running a loss, he needs to know what the number of plain shirts he would have to sell to break even. And again, break even is when your costs for running business matches your income. The revenue is what it's called. And in fact, there's two words that often get confused, and that is revenue and profit. So revenue is just any money coming in. Profit is after everything is calculated, your costs as well. How much money you made at the end of the day, pretty much. All right, so let's see. Set up our equation again. Or inequality. I keep saying equation, even though it kind of acts like an equation. I have to say the word inequality. All right, so let's see. He sold 90 shirts and $7 a piece. So that's, well, 9 times 7 would be pretty easy. That'd be 663. So it'd be $630. And I'm gonna have to do some algebra here. So again, this is just some basic algebra. So I know sometimes it's kind of weird when I just sort of switch things from one to the other. But I am gonna minus 630 from both sides. So this, if I remove the cost that we already know we have, or the profit from, not the profit. So again, we already know that just as the day started, this guy already made $630 already. How much would he have to sell a regular shirt? So in this case, it would be, he'd have to sell about $570 worth of the plain shirts. And since they're $5 a piece, I'm gonna divide both of them by 5. And the number of plain shirts would have to be greater than 114. Oops, I put a plus sign instead of this thingy here. So there you go. The shirts must be, well, actually in this case here, it would be or equal to, because break even literally means that you can get exactly that amount. So since if this guy manages to sell exactly 114 shirts, he will break even. But after that, after the break even point, everything after that is profit. So that's the money he gets to take home. So this business is probably not a very, well, just the way the numbers are going, it doesn't look like it's running that well for him. Because, well, I guess, I mean, if he can sell 150 shirts in a day, 114 wouldn't be so bad. But sometimes with businesses like this, it's really the big orders that make the difference. The big orders are where, you know, where the meat and potatoes comes from. Anyway, so that's it for that. Now we're gonna have to think about this a little bit later in the course, but we're gonna switch gears and move to something else. We are gonna go into graphing linear inequalities. So with those, it was kind of hard to tell, you know, if we know certain things, like we know how many graphic shirts or plain shirts, we'd have to do a little bit of solving and plugging in and evaluating and all this stuff. But what if we could just point to an area on a graph and say, okay, well, if we get into that area, we're good. Or if we stay in this area, that's good. So that's what we're gonna do now. We're gonna kind of use graphing to show what I call the solution area. So that way you can easily just spot an area where you can know that you're going to get a true statement. So as they explain it, graphing a linear inequality is a visual way of showing the ordered pairs that satisfy the inequality. So again, basically you just point to it and say, okay, that's going to work out. So what the steps are: put the inequality in slope-intercept form. Now be sure to foot the inequality if you multiply or divide both sides by a negative, or everything by a negative. Graph the line is the next step. So this is pretty easy. Just use your y equals mx plus b, which is what slope-intercept form is, right? Yesterday I made excellent breakfast. Start with breakfast, use your slope. But there's a little bit of extra information here, and that is to use a dash line for less than and greater than symbols. And we would also use a solid line for less than or equal to and the greater than or equal to symbols. All right, so this might be a little bit confusing at first, but it's going to be kind of tied into what we've already used. So if you remember, we've had some exercises where we have a number line and we would use an open circle. I'm going to just make up a number here. So like x is greater than 5. All right. So if this was 5, right here, we would use an open circle and we would point the arrow to the area. That would make this true. So if I plug in 6 or 7, that'll make it true. And then we also used filled circles or closed circles. So in this case here, if I said that x is less than 9, so I'm going to say that this area is 9, then that means this area will be all of the areas that will make this true. But you, again, remember in this case here, we're talking about open and closed circles. So with a open circle, I cannot pick that area. I cannot pick the exact area. So in this case, if I pick 5, 5 is less than 5, that is false. All right. And if I pick, in this case, if it's a closed circle, we would get an or equal to. And if I pick 9, so 9 is less than or equal to 9, well, in this case, that would be true because the or equal to allows it to be the same number. And that's the same thing that makes the difference between the dashed line and the solid line. All right, so hopefully that kind of explains it. The last step would be to shade above the line for greater than or equal to symbols. And then we would shade below the line for the less than or equal to symbols. So there's a little bit. Now again, this is kind of like, which way does it go? Does it go, to the right, or does it go to the left? And this is a one-dimensional thinking, right? It can either go left or right. And you've probably heard this term before of two-dimensional. So two-dimensional means instead of being able to just go left and right, we are also able to go up and down. So let's go ahead and graph these. Hopefully graphing it shouldn't be too much because this one is already in slope-intercept form. So y equals mx plus b, even though this is not an equal sign. Okay, so since it's not an equal sign, well, there's a little bit of an extra step, but we'll get there when we get there. So let's graph it now. All right, let's graph it. So start with our regular number because, again, yesterday I made excellent breakfast. Start your day with breakfast. So that means we're going to have to start here at -1. From here, we follow the slope using our rise and run, especially if it's a fraction. So most slopes are going to be fractions, and it's kind of a good thing because it allows you to find out which way it's going to go. So up 2 over 3, up 2 over 3. Now when I graph, I like to have at least 3 points of reference, right? I got to line this up using 3 points, and that's usually a little bit more accurate than just using 2. But I like to have 3. Okay. So now we know at least where this line is going to go. Now again, double check your line. Make sure that if your slope is positive, okay, positive slope means it's going up. So that's like the easiest thing that students mess up on, is that they make, for some reason, they make all the slopes go in the same direction. No, not all the slopes go in the same direction. Easiest thing you can do is check to see if it's a positive or a negative and make sure it's going in the right direction. Next is for graphing, is that we have to use, again, dashed line or solid line, so that you find that out by seeing, does this have an or equal to? So in this case, this does not have an or equal to, so we would use a dashed line. So I'm going to do my best to try to connect these 3 dots. All right. I made it look easy, but it wasn't. Okay. Now, we graphed it using the line. So next thing we need to do, the third step, is to shade above or below the line. So sometimes, and this is another thing that students sometimes have trouble with, it seems easy, but I'm pretty sure, you know, it'll probably help some of you watching this. But here's an easier way that I think about it. All right, so look at the mouth. Remember, like your elementary school teacher might have told you that number wants to open towards the bigger number, right? Whether it was a monster or an alligator or a Pac-Man. In this case, it's open away from the Y, right? It's open away from the Y. So here's the Y, and now almost every graph has this Y, okay? It's just the way it is. I don't know why they, well, I know why they do that, kind of. You know, it makes sense that it's the top. That's the positive direction for the Y-axis, is going up. So they put the Y on the top so you can easily spot it, where if it was on the bottom, it would be harder to see, or you probably wouldn't see it right away. But anyway, this is the Y we care about right now. This mouth is open away from the Y. So when I shade it, I'm going to shade away from the Y. So if I were shading on the Y, towards the Y, I'd shade the top of this line. But now I shade the bottom because, again, it's the side opposite. Or again, it says it in the directions that, you know, if it's towards the Y, you shade on top. And that's a pretty good way of explaining it too. In fact, I'll probably do a little bit of explaining on what it means by the bottom of the line and the top of the line. So anyway, that's it for this one. Let's go ahead and move on to the next one. So this one has a couple of things that make it different from a typical linear format, linear formula. I keep wanting to say linear equation because that is the common way to say it. And I don't feel like saying linear inequality, linear function maybe. Anyway, this one here does not have a number. Well, it does, it's 0. So in this case here, it starts right from the middle. So I know some students that might look at this and say, oh, that means it doesn't start anywhere. That means we have no line. No. You can add 0 because that's identity property. Remember, adding 0 does not change anything. And if I put a 0 here, that's going to show you very easily that that's where you go essentially. Anyway, next thing we're going to do is I'm going to make this into a fraction by putting a 1 under it. And this is also identity property because dividing something by 1 also does not change the value of a number. So this allows me to find the rise and the run. So remember, rise over run. So this means that we rise in a negative direction. So go down 4 over 1, down 4 over 1. And again, I like to have at least 3 spots of areas to graph, reference points. And check your line, make sure that if it's negative, it's going down, which in this case, it is going down as we move left to right. Simplest thing, but I get so many students missing this. It's like a little bit, drives me crazy, okay? It's very easy to do, but people mess it up all the time. All right, so now in this case here, I managed to draw the solid line. Now, you also want to make sure these lines are very straight. So use a ruler. If you don't have a ruler, use something else, okay? Go around I'm pretty sure if you're at home or somewhere, you probably find a piece of paper. So just find a piece of paper and use that as your ruler. You know, you could probably find a card or something that would be rigid enough to draw a straight line on. And the other thing is, make sure you draw the line all the way from one side to the other side, okay? We don't need these little tiny lines that just do this, okay? In a regular class, I would probably mark those as wrong if you have those little tiny lines. Lines go all the way from one side to the other because they go on forever in both directions. And that's why they have these little arrowheads at the ends, because they go on and on forever. Okay, so that's enough about the two basic things about what I need from graphs that drive me a little crazy, that people always mess up on. Well, not always, but enough times that it does drive me crazy. So let's go ahead and do this one here. We got to shade it now. So look at the mouth. It is open towards the Y, so we shade towards the Y on top of the graph. So start here, shade, see, starting right there. And I'm going to shade everything on this side of the graph. Now, if you're doing this, you can just use a pencil, okay? I would suggest using a pencil. Sometimes I will get students that use highlighters or colored pencils or something to make it look a little bit nicer, sort of like the way I have my graphs here in green. But the problem is if you decide like, oh no, I shaded the wrong side, you know, how do you erase a highlighter? So I'd kind of suggest using something like pencil is probably the best to shade it in. All right. Now, I also said that I was going to talk a little bit about the top of the graph versus the bottom of the graph. So thinking about the top and the bottom shaded, so that's what it said in the direction. So this is a second way of thinking about the problem. So thinking about it, the first way was look at the mouth and shade towards this Y on top or bottom. Now, if you go to a park, they oftentimes have these little shade houses. I think the word is gazebo. I don't know why but they usually have a regular looking roof held up by these poles. And they usually have a picnic table in there. And then they usually have like chairs or benches or something, you know, because people sometimes want to eat in the park, but they don't want to sit on the ground and they'd rather be in the shade. And the roof is there for two reasons mainly. So the first reason is to keep people out of the sun. Right? So when the sun is shining, they want to be out of the sun. So in this case here, we want the bottom part shaded, just like this graph here. If the sun is up here, we want the shaded area. We want the house for the shade. Now in this case here, in the second example here, the top part, we want to keep the top part out. So if it's raining, that gazebo is going to protect you from the rain so you can stay dry. So in this case, the rain is on the outside, right? And then in here, the shade is on the inside. So that's kind of a way of thinking about it, because again, rain and the sun usually come straight from the top downwards, okay? All right, now that also depends on the sun, but you know, usually it's around noontime is the time you want to stay out of the sun, especially on a hot day. So anyway, that's how you think about it versus up and down. All right, so it's probably going to go a little bit faster after this now that we got a little bit of the basics out of the way. So let's go ahead and speed this up a little bit. Now, for this one here, it is not in slope-intercept form. We want to put it into slope-intercept form because there's a lot of things that are very helpful. Now, we could graph this one in standard form, but well, we'd have weird intercepts. We'd have 12 divided by 5 for the x-intercept, and that would be something like 2.4, you know, and we'd have to graph 2.4 as best we can on there. So it's good for finding the intercepts, but it's not very good for finding out where the line goes exactly. Now for some of these, we need to know exactly where the line goes, and usually slope-intercept is a far more accurate way of doing things. So let's go ahead and make it look like y equals mx plus b by moving some of these numbers around. So I'm going to minus 5x from both sides. And now 3y is by itself. Negative 5x is on this side, and 12 is positive, so it's going to be plus 12, right? And then the 5x is negative, so it's going to stay negative 5x. Okay, now I'm gonna divide everything by 3, and the reason, again, is because I want this y by itself. That's how you solve for y. And let's see, I have a fraction here, so negative 5 over 3. And then 12 divided by 3. And again, usually your slope is going to be a fraction. That's somewhat of a good thing. Okay. So let's see. Let's go ahead and graph this one here. Plus 4. So that's where the line begins. Again, y equals mx plus b. B is for begin, so begins at 4. Now we have to go down 5 over 3, which would be right about there. And I could do this again, so down 5 over 3. Okay, yeah, close enough. All right, now we got to pick the right kind of line. In this case here, this is telling us that we need a solid line because again, it has the or equal to. Now sometimes I'll get that, I'll get this, okay, so what does it mean by solid line and dashed line? You know, so hopefully I can think of an easier way to explain it. But we'll see if we have time. Anyway, so there we go. We graphed the line. The last step will be to shade the correct side. So now I want to shade. So again, is it going to be on top of the graph, which would be up here, or do we shade on the bottom of the graph, which would be down here? Now, once it's in slope-intercept form, okay, it's got to be in slope-intercept form because slope-intercept form tells us a lot more about what's going on. So look at the mouth and let's see if it's open away or towards the y, which in this case it is away from the y. So that means that we go away from this side. So we don't want to touch this y on top. So I'm gonna have to shade the other side. There you go. So we shaded the side away from the y on the top of the graph. All right, so I think we're done with that one. Let's go ahead and move on to the other one. So I'm going to go ahead and start to get this one into slope-intercept form. So again, looking at the mouth, it's open away from the y. So you might think, well, we shade the bottom of this graph. Okay, well, let's find out. Do we shade the bottom of this graph? Because remember what I just got done saying, we wait until it's in slope-intercept form before we decide which side to shade. Because this is the part you got to worry about. Anytime you're dealing with any type of inequality, in this case here, I have to get rid of this negative 6. So I have to get rid of the 6 and I have to get rid of the negative because I cannot have anything by itself. I mean, I have to have the y by itself. I can't have anything, including the negative. And what this is going to do is that it's going to flip the sign. All the signs. Everything that is positive will become negative, and anything negative will become positive, but the sign of the inequality will also change the direction. So that's one of the things we got to do is switch that. And again, this is one of those really important things that people seem to forget quite often, but that's like one of the only things that really makes an inequality different than solving an equation. Because if we, again, multiply or divide by a negative, then we have to flip the sign. Adding and subtracting doesn't change it. So I know sometimes students will say, oh, well, I subtracted both sides. That means I have to flip it. No, only when you multiply or divide because all the signs are going to change. So this was negative, now it's positive. This was negative, now it will be positive. And this 12 was negative, or the b value was negative, now it shall be positive. Okay. Now if we look at it, the y, the mouth and the y is open, you know, the mouth is open towards the y. So graphing it, mark out the b value, so 2 in this case, and then up 1 over 6. And I said I like to have 3 points of graph. Okay. Now I can't go anymore because that would take me off the graph, but if we look back here, negative over negative. And you've seen me do this before when I would take a slope and reverse the sign on both of them. So in this case, I have down 1, back 6. And now I have a third point that I can draw a line through. So when I get my ruler, I have, you know, having it wider apart makes it easier to graph it more precisely. Now in this case, I'm going to need a dashed line. So again, the type of line is important because it says it in the directions. And it's also just important for everything, okay? Everything, all kind of work. All right, so we graph that as best we can. Now, again, looking at it here, that's not going to tell us the whole story. That's why we have to wait until it's in slope-intercept form. Because if we looked at it here, we might shade the bottom of the graph, but looking at the mouth, it's open towards the y, so we have to shade the side with the y. So start from here and start shading the side and then stay on that side of the line. And there we go. So that is it for that one. Now a quick kind of thing on the lines. So sometimes I get this question, you know, what about the dash line and the solid line? What's the difference? So think about it like a cliff, okay, right? So cliffs are dangerous. And you've seen some cliffs, and usually when you see them in a movie or a cartoon or something, they're really straight, right? There's a really clearly defined edge. And I don't remember, but I think Horseshoe Bend was like this. There's kind of a well-defined edge. So you can pretty much walk up right to the edge of the cliff and look over. It might have changed a little since the last time I've been there. But then you have a lot of cliffs in real life that will usually kind of have a jagged edge. And these kinds of cliffs are way more dangerous to go to the edge on, right? Because it's very easy for you to slip. So on a dash line, that means don't go near the edge. And on a solid line, it means you're okay to go to the edge. So if you pick an area on the line, like if I pick here, that should be a true statement. If I pick an area on this line, like if I were to plug in the number over 6 up 3, I would get something. I'd get, what would I get? Well, okay, let's try that out. Up 6 over 3. I'm sorry, over 6 up 3. So I'm going to plug it into here. So y is 3, 1/6, and then x value is 6 plus 2. And now multiply the top number, or again, if you want to, you can also just put a 1 under it. But I have 3 is greater than 6 over 6 plus 2. And we know that 6 over 6, or 6 divided by 6, is just going to be 1. So 1 plus 2 is 3. So I get 3 is greater than 3. That's false. So that's why we can't pick an area right on the line, because that would be false. If I were to pick a spot right on the line, like in this case, I know this spot is right on the line, Maybe we could try this one out. So what is this area? So to test it, and you don't need to test it all the time. In fact, actually, I'm going to show you another way. You can also check which side should be shaded. So this is over 3 down 1. So I'm going to plug it into here. So -1 greater than -5 over 3 times 3 plus 4. So again, plug in your x and y. And here I get 3 times 5, which is 15. So -15 over 3 would be -5. And I'm going to do this a little bit faster because I'm just showing you why we use dashed line and solid line. So in this case here, I get 4 minus 5 is -1. Now, in this case, I get a matching set of numbers on both sides. But because this one has the or equal to, that means it's true, which means I can pick an area right on the line. And on this side here, we cannot pick an area on the line. So again, that cliff is a slippery slope. All right, so hopefully that kind of explains why we use dashed lines and solid lines, because if you pick an area on the line, they will come out to be the same number on both sides, but the or equal to is the thing that will make a difference. All right, so let's go ahead and move on to the next one. So same thing with these ones here. We are going to need to put it into slope-intercept form. And I got to get this x out of here. So 12y greater than -9x. And the 60 is also negative. So that means I'm going to have to put that in there, just like that. And it looks like I'm going to have to divide everything by 12. So y, right, that's got a 12. So 12 divided by 12 is 1. Now, in this case here, if I were to go down 9 over 12, I would definitely go off the graph somewhere over here. But that's why we reduce our fractions. So let's go ahead and reduce this as a fraction. And that's going to be, well, 9 over 12. So 9 and 12 can both be divided by 3. So that's what we're going to do. We're going to divide both of them by 3. Now, don't forget the negative. 3 over 4. So 12 divided by 3 is 4. So x here. And then 60 divided by 12. That's going to be 5. So put 5 here. And it looks like we are set for graphing this now. So go to 5 here. So that's where the line is going to start. And we also have a negative slope. So this means the line is going to go downwards as we move left to right. So down 3 over 4. Down 3 over 4. And I like to have 3 points. You might have enough to graph it here, but again, just to improve the accuracy of your graph, let's go ahead and I'm going to do one thing. Now, remember on the other one, when we did this, we had to make both of them into a negative and go back the other way. So for this one, we're going to switch the negative, because in this case, this is -3/4, which is like -0.75. We can change the direction by moving the negative from the top to the bottom, or the other way around. So if we look at this, now my rise is 3, which means I go up 3, back 4, and it stays in this line. It would stay on that line. So again, that's just a quick way of being able to get an extra point of reference for your graph. All right, so now we gotta graph it with a solid line, because this one has an or equal to. So again, that means it's a nice solid edge that you can go up to. And then shading it. So we got to shade the right side. So again, looking here, once it's in slope intercept form, it's open towards the y. So start shading it from the y. All right, there we go. Got a nice outline going, so I should probably be able to fill this in. And like I said, you can probably use something else to shade it in if you're very certain that you know which side is best to be shaded and all that stuff. But if you think you're going to make a mistake, use a pencil in case you need to erase it. And there you go. Now you can also check where, you can check to see if something is true or false. So this is a third way of determining whether the top or the bottom is going to be the shaded side. So again, I've showed you the mouth open towards the Y method. The packet tells you if it's open as a greater than, it's the top of the line, and a less than is below the line or something like that. But there's a third way, and this is if you're really not sure. Okay, let's say you just don't know. You can pick a test point, just like we did with the last one, but in this case, I'm going to pick one that's definitely on one side of the graph. So in this case, my test point will be 1, 1. And I'm going to plug in 1, 1 right here. So 1 is Y, and I'm going to make it easy because anything times 1 should just be that number itself. And just to keep things going, I'm going to turn this into negative 0.75 minus 5. And we get something like this. And then we check if it's true or false, which in this case, this is true, because even though 5.75 is normally a bigger number, in this case, it's a negative number. So positive numbers are always greater than negative numbers. So this is a true statement. Anywhere in the shaded area is true, and anywhere on the outside is false. If I were to pick, say, -5, or something like that, that would come out to be a false statement. The mouth would be open towards the smaller number. So that's just a kind of another way you can check it. Or, sometimes I also tell students to just do that as well. That's usually the best way to do this, is to check it. Just like when we were using the open circles and the directions with the arrows, I told people check it. Try not to rely on any sort of gimmick methods to solve it. Anyway, let's go ahead and do this next one here. Now, this next one here is a little bit of a tricky one because we can't turn it into slope-intercept form. Now, I did just mention that we were talking about using the open and closed circles and picking a direction. Think about what the graph for this one would look like. It would look something like this. Right, we would use an open circle, and then we have to pick one direction the arrow goes to. So in this case, we are looking for x values less than -4. So if I'm looking for numbers less than -4, I have to go to the left, because left is less. All right, so that's what it would look like if we were graphing it on a one-dimensional graph. One direction, so left or right. But in two-dimensional, we can go left, right, and up and down. So graphing this, we could mark out -4, which would be right here on the line. But what would it look like in this case? Now remember what I was also saying about graphs that are lacking a x value or a y in their function. So in this case, there is no y, which means it does not touch the y-axis. The only way you could make a line that does not touch the y-axis is to make one that is parallel to it. I'm going to move it over just a little bit so you can see it a little better. And there you go. So again, open circle is kind of a lot like the dash line. They're very similar in how they are used. And that would mean everything on this side is shaded. And if you're not sure, you can pick a test point. So in this case, if I pick, say, -6, -6 is less than -4. This is true. And again, if they're both negative, you want the one that is less negative. Just like if you have to choose two bad options, right? If somebody is telling you that they have to punch you, are you going to get punched in the face or are you going to get punched in the arm? Or if you're falling down, are you going to put your hands in front of you to try to stop yourself and probably break your arm? Or are you going to allow, you know, your face to land on your face? So again, in those situations, bad things are happening, but you got to choose the one that is less bad. Which one can you live with? All right, so anyway, we're done with these two. So hopefully you learned another thing from this one, and that is to test an area in the graph to see if it works or not. All right, so let's go ahead and move on to the next set of exercises. Application. So how does this, you know, how do we use this in something that could help us in our everyday life? All right, so this is kind of an older example, but I remember when I got my first phone, my first cell phone. I don't think people even call them cell phones anymore, actually. I think people say mobile or mobile device or something like that. Because nowadays your phone is not really a phone anymore. But I remember back in 2008, you know, you had like text messages and you had to like push the 5 button like 2 times to get K or something like that. But anyway, back then they used to have this thing here. I'm not sure if it's still like this. But I know they would charge you for the text message. So in this case, this person, Stephanie, gets 10 cents per text message charged and 25 cents for a picture message on her cell phone. Again, I don't think it's really like that anymore. In fact, I think more people are moving over to like Instagram and stuff for pictures. Her monthly budget is $30. Now, I'm going to kind of change this up a little bit because like I'm going to make it a little bit more updated. So like my phone, like data, there you go. So data can go up to a certain point, and I don't have unlimited data. I think mine's like 4 gigabytes a month or something like that. As long as I stay under that, my bill doesn't go up. So we're gonna say that as long as she stays under $30, her bill will not go up. So let's write a linear inequality to represent this situation and then graph it. So for here, we have 10 cents. Well, let's identify our variables. Since we're going to be graphing it, we're going to use X and Y values. So in this case here, X would be the text messages, and the other one would be the picture messages. I'll just call it picture message, not pictures, because I think we're only going to be sending one. And then, let's see. Set up our equation now. So 10 cents per text plus, what does it say, 25 per picture message. And let's see, normally what I would do is I would say, let's just do this and then see which way works out better at the end. But I think I kind of confused my other class a little bit with this. So we're gonna have to find out which one is it. Is it gonna be this one or this one? And this is usually when you're coming up with word problems, this is usually the part that I think some students, like the highest amount of them, will generally have trouble picking which way the inequality opens towards. So think about it. Think about what both sides represent. So this is her budget and this is her cost. Which one do we want to be bigger? We want this side to be bigger because we want this side to be smaller. So again, it's kind of like data. In my example, I know I have 4 gigabytes of data by the month. So if I use 3 gigabytes of data, my bill does not go up. If I use exactly 4 gigabytes of data, my bill does not go up. If I go even a little bit over, my bill goes up. If I go like 4.1 gigabytes or something, 4.01 gigabytes, my bill goes up. So that means we want this side to be the larger side. Now we're also gonna have to change this to be slope-intercept form. So I'm gonna minus 10 from both sides, this 10 cents. So now it's gonna be negative 10 cents. And the 30 is still gonna be there. Now here's kind of where decimals don't really work out. All right, so you've heard me say this before where I was talking about decimals and fractions and why sometimes we need fractions. Because in this case here, I'm gonna divide everything by because I got to get this y by itself. So that means I'm going to have to divide everything by 0.25. And this should give us our new y value. So y in this case should be less than. Okay, so getting back to this point right here. So if I were to get a calculator and see what it does, because I know that's what most students want to do. They want to run to a calculator because they're afraid of doing their own work. If I were to take 10 cents and divide that by 25 cents, we get this weird number, 0.4. Now, does this help us graph a slope? Not really. I mean, I guess you could. If you wanted to graph, say, over 0.4 down 1 or something like that, oops. You know, you could do something like that. But here's where fractions win out. Because, you know, you can't go, okay, let's see, 0.4 is right here. The next 0.4 would be right there. The next 0.4. Maybe if you were very precise, you could do something like that. But let's go ahead and do this. So 10% or 10 cents over 25. Now I'm going to multiply this by 100 over 100. So I sometimes I get students like, well, why would you do that? Well, don't forget 100 over 100 or any number over itself equals 1. So if I grab a calculator and take 100 divided by 100, it's just 1. Timesing something by 1 is identity property, so it's not actually changing the value of the number. It's just changing what it looks like. But why multiply it by 100? Okay, so if I multiply 10 cents by 100, I get 10. And then as my bottom number, I get 25. So that basically just has the effect of moving my decimal all the way to the end. So by moving the decimal all the way to the end, I get a whole number. Now these two numbers are exactly the same thing. If I were to take 10 and divide it by 25 on a calculator, I would still get 0.4. But I want to reduce this number. So we're going to reduce it just like we do with any other fraction. Find a number that will divide both numbers. So 10 can be divided by 5 and 25 can be divided by 5. So now I have a much better number to use. So again, this is another area where fractions win over. Anyway, so let's see, $30 in quarters. And again, you could use a calculator, but in this case, $30 worth of quarters is going to be 120 quarters. And if you were doing this by hand, you'd have to do something like 30 divided by 0.25. You'd have to change it so you'd basically multiply both of them by 100 again. And again, I think that's one of those things that I run into students that won't be able to figure that out. And it's not really that important because again, it's not like in the 90s when teachers would say you're not going to have a calculator in your pocket at all times. But math isn't always about what you know, it's about what you do with it. And it's also about the lessons you learn from it. So even though you know how to do something or you know how to find it on a calculator, sometimes it's just important to have the lesson of what it means. All right, so I'm going to go ahead and label the graph because I'm going to have to graph it. So that's 20, this would be 40, 60, and I probably don't need to have all of these graphed out because that would take a little bit of time. So anyway, to graph it, I just need to know, because remember, X is the text. So that means this axis is the text messages. And these are the picture messages, the Y. And again, there's supposed to be a Y up here, but this one does not have a Y up there. But we do start from 120. And then we go, oh, actually, hold on. You know what? I almost forgot this. I almost forgot the negative on that because I was too busy looking at the fraction and ignoring the negative. But luckily I noticed that. So down 2 over 5. Down 2 over 5. And this should be enough to finish the line. So again, make sure that line goes all the way across. Now there's actually also another thing that we have to consider here really quickly. And that would be, does this have an or equal to or not an or equal to? So I kind of glazed over this really quick, and that was, with my data, I get 4 gigabytes. Now, if I manage to, at the very last day of my data cycle, if I manage to use exactly 4 gigabytes, I don't pay anything extra. But if it goes even like one little piece over, then I have to pay more. So in this case here, she can, if she manages to pay exactly $30 of her budget. So again, $30 of her bill is set aside for these messages. If she manages to land exactly on $30, she doesn't have to have her bill go up. So that's why we would use a solid line for this one. All right, now the next thing we got to do is shade one of the sides. Now remember, this is a budget, meaning that this is where we want to stay. So sometimes with that, just enough with that information, you can kind of tell where it's going to be. You could plug in some information, like if we were to say, okay, well, what if we sent 20 texts and 20 pictures? Well, she'd still be under budget. And in fact, that would actually be enough to, just from there, we would be able to figure out that that is a possibility that will work out and stay under budget. So if she manages to send only 20 pictures and 20 text messages, then she would be under budget. All right. Or again, we could look at the mouth and say that it's opening away from the Y. So if this line were to continue on, which it doesn't, because you can't send a negative number of text messages. You can't send a negative number of text messages, so it wouldn't go over here anyway, but it would be still away from the Y. It would still be the bottom side of the Y. Anyway, so there we go. We got that one. Now, using the graph, give 2 possible combinations of text and pictures that she can send to stay within her budget. So they just want to, just any number, okay? So in this case, we could probably say something like, say she sends 80 text messages, right? If she sends 80 text messages and say 40 pictures, that would be right here. That's still inside the budget. So this is why it's a good idea to have a graph, because we can easily see if she sends 80 texts and 40 pictures, PICUs, she would still be within the budget. And if we were to pick another number, like maybe if we were to pick something exactly on the line, that would also work out. So she would probably send a lot more text. So in this case here, I have 100 texts. So I just didn't want to write all this out. So let's say that, for instance, she sends 100 text. Oh, I noticed I put test in there. It's probably because in my day-to-day life, I write the word test a lot, so that's probably why I keep wanting to put that in there. And if she sends 60 pictures, man, what is that with my typing today? She would still be within budget because that is this dot right here. In that case, she would land exactly on 30. So, if she's counting her text messages, or maybe she has a part of her phone that says you have sent this many texts or this many pictures, and she's, it's the last day, and the next night, overnight, is the cycle is going to reset itself. She might say, well, I could send a few more pictures and a few more texts, and it'll be exactly 30. In that case, her bill would not go up. So again, that's just, you can easily see where the possibilities are. All right, let's get to the last one. So last example in this one here, and then we'll go ahead and call this one a day. All right, so Scott makes $12 per hour babysitting and $8 per hour working at the grocery store. So again, a person with 2 jobs again. He will need to make at least $600 to buy a new computer. Okay, so we are talking about X's and Y's because we want to graph this, and you could probably send something else. You could have like B or G for grocery store or something. But since we're graphing it, it just makes a lot more sense to say X's and Y's, which I don't usually like X's and Y's when working with word problems. But unlike the example with the t-shirts that we had at the beginning of the lesson, we weren't graphing that one. If we were graphing it, I'd say let's convert those t-shirts into X's and Y's. All right, so here we got, oops, what the? Babysit. Oh man, what is up with my typing today? And then Y is grocery store. There you go. Now we got to write an equation that works this out. So 12x, because X is babysitting, $12 an hour at babysitting. So one hour of babysitting would be $12, 2 would be 24, and then 3 would be 36, and so on. Now we also have to compare this with 8 hours at the grocery store, which in this case we assigned the variable of Y. Now again, I'm going to put an equal here, but be careful because we're going to come back to this in just a minute. We need to make $600, or this person needs to make $600 to buy a new computer. Now we're going to have to turn this into y equals mx plus b into a slope-intercept form. So first thing I'm going to do is move over. Oh wait, no, I'm sorry. I almost forgot again. We're going to have to replace this with an inequality. So which side do we want to have be bigger? So let's think about what this means. This means he earns this much money. Let's say he makes $500. Now in this case it would be true, but can he buy the computer if he made $500? So this is, again, when writing word problems, this is usually the part that most students will have difficulty getting, and that is, which way does the mouth go? So this is his earnings, and this is his goal. His earnings need to be higher. So in that example where I said, what if he had $500? Well, he would not be able to buy the computer. Well, what if he made $700? If he made $700, then he would be able to buy the computer, and it would be true. Not only would he be able to buy the computer, he would also have some money left over for other things. So this is the right way. So whenever you're setting these up, again, think about which side you want to have be the bigger side and which side, think of some numbers to plug in there. What if it was this? What if it was that? All right. And again, as humans, that's one of the best things we have. What if, because we always like to imagine what if this and what if that. That's how we make the world better for ourselves. Okay, so let's go ahead and move this over. So I'm going to minus 12x from both sides, and that's going to give me negative 12x. And again, I am going to have to divide everything by 8. So just to make things go a little bit easier, I'm going to show this step here. So divide everything by 8, and I should have a y value that I need. And y is greater, oops, that's not the greater button. There we go. So y is greater than what we need to have on this side. So what do we have on this side? So it's definitely a negative number. Oops. It's definitely a negative number, and 12 and 8. So we simplify that. Divide them both by 4. So 12 divided by 4 is 3. And 8 divided by 4 is 2. Plus, and here it looks like we have 600 divided by 8. So let me get my calculator. And that would be 75. So there we go. We have our graph set up. And I'm going to have to come up with a way of making this work. So maybe we'll have each of these be 5. So 5, 10. This would be 20, 30, 40, 50, 60, 70. And I managed to get 75 right there on the top. So we know that this graph is going to literally start from the very apex of this graph, or the very top of it. And then we go down 3 over 2, down 3 over 2, down 3 over 2. And I'm just doing a lot more just because it's kind of easy to do. But we can see that the line kind of goes down. Oh, and we also have to decide, is this going to be a dashed line or a solid line now. Now, if he manages to make exactly $600, would he be able to buy the computer? Well, ignoring taxes and all that stuff. Or maybe the computer is actually $550, so he already factored in taxes and all that stuff in there. Okay, but in this case, if he manages to get the exact amount of money for the computer, yeah, he will still be able to buy it. He will be broke, but he will still have it. And in this case, the computer is probably the more important thing. So in this case here, we will use the or equal to in our graph. So that means that we will need a solid line to graph this. Now the other thing is, where does the shaded area go? Does it go here or is it up here? And again, sometimes you can just think about this. Let's say he works several hours at one of the jobs. So in this case here, this would be, let's see, X is babysitting. And this is the store. We'll just call it the store. So if he makes, 50, if he works, 50 hours, I guess. So if he works 50 hours at babysitting, he will have enough to get the computer. But again, he has to kind of balance both jobs. So most jobs are going to schedule you for about, well, actually it'd be like 20, if we're talking for a week. But most jobs don't pay by the week. Most jobs pay every 2 weeks, which means 40 hours. So if he worked, let's say 40 hours babysitting and 40 hours at the store, he would have enough money to buy the computer. So in this case here, we could also just use this thing here. So remember, that means it's open towards the Y. But since it's right on the thing, that's going to be kind of hard to tell. Okay, so which side is it? Well, just imagine this line kept going, and now you can see which side the Y is on. But again, sometimes you won't see the Y or the top here. So in this case, if it was raining, this would be the top of the graph. So that means, again, the top of the graph is the shaded side, the top of the, the top of the line. Okay. And do my best to shade that in. And it says here, using your graph, give 2 possible combinations of the number of hours Scott can babysit and work at the grocery stores to ensure that he can afford the new computer. All right, so as long as we're in this, green area or shaded area, which I just shade as green, he should be able to buy that computer. So like I said, there are some different, I mean, I kind of want to be realistic about this. So we could say something like 70 hours of babysitting, but that's a lot of babysitting. And a lot of times babysitting jobs are usually not that long. A lot of time, well, I mean, unless the parents are like out practically at work or something, and there's absolutely nobody to watch the kid. But again, in most cases of babysitting, it's usually like going to a movie or going to, dinner at a restaurant or something, and then they come right back. It's usually like 2 or 3 hours, maybe 4. So anyway, let's think about that. So he could do 20 hours of babysitting maybe. So where would 20 be on this graph? So it would be 10 and 20. So 20 would be right here. So if he did 20 hours babysitting, so let's see how much he would have to do just to barely break even. So if he did 20 hours, he would have to do about 45 hours. And what did I say? 45 hours. Grocery store. And this is not completely unrealistic because a lot of times people will get overtime. So if you work more than 40 hours a week, you will get overtime, which means they pay you a little bit extra after each hour, after 40 hours. So it's not entirely unrealistic in this case, but I think most stores would prefer to keep their employees under 40 hours. And in fact, one time I had a job I once had a job and they would not schedule you for 30 hours, although most of the time I would work 35, 36, 38 hours or something like that. But they didn't want to pay overtime. So overtime is kind of a cost that they really don't want to have to pay everybody. So sometimes, like in my case of that job, they would only schedule you for 30 hours. And I think it's like that now. I don't know if Obamacare is still a thing, but I know that during the Obamacare thing, they were talking about, because if you work 40 hours, they have to give you health insurance. So let's say in this case here, 30 hours at the grocery store. So he knows he can get 30 hours at the grocery store. How much would he have to babysit? So if this is 50, and I didn't fill out my graph all the way, he would have, could he do 30 hours? Like, let's see, maybe just a little bit over. Yeah, he could do 30 hours because that would be right here. So 30 hours would work. So 30 hours at both jobs would probably work. And there we go. But again, anything in there is going to work out. Now, is it, I'd like to keep things realistic because I really don't like to think that someone's going to work 100 hours in 2 weeks babysitting. I mean, I don't know how people can be parents sometimes, like, because it's like babysitting, but it's like all the time, you know, like, I don't know. Sometimes I watch my nephews and I watch them for like a day and I'm already tired of them. And they're constantly trying to get themselves hurt by jumping off of things and touching things they shouldn't be touching, or handling things and running outside. And like, man, how the heck do parents deal with this sort of thing? I don't know. Maybe they're nicer around their parents and they think of me as the person they can goof off with or something like that. I don't know. But anyway, that's enough about that. Let's go ahead and wrap this up. So let me go ahead and I think what I'm going to do this week. So that wraps it up here. So I'll see you next time. Okay, bye-bye.